Hi everyone, and welcome to the third part of this video series on semiconductors. Today we'll be talking about doping. And so let's just start with an intrinsic semiconductor, which is a semiconductor that is undoped. So it has no impurity atoms and the electron hole pairs are only created by thermal energy. So as we have said from the previous video, when the electron from the valence band gains enough energy from thermal energy that is larger than the band gap energy of Eg, it can be excited to the conduction band, and that's how the electron hole pair is created. So in the intrinsic semiconductor, the electron concentration in the conduction band, N0, is equals to the hole concentration in the valence band, which is P0, and this is equal to the intrinsic carrier concentration, which is Ni. So about the intrinsic carrier concentration, we'll look at it more in the next video, but for this video, it's not that relevant. And so let's look at doping. N-type doping is where you introduce group 5 donor impurities. So for example, I'm just going to use phosphorus in the example. And then for P-type doping, we introduce group 3 acceptor impurities. So as you know, most semiconductors are group 4. Oops. They are group 4, or if they are compound semiconductors, they are group 3 and group 5. So also like it's also 4, so 4 electrons. And then when you introduce group 5, there's an excess electron, and when you introduce group 3, there's a lack of an electron, so an acceptor. So this is why they're called donor impurities and acceptor impurities. I'm just gonna start with N-type and just gonna draw a silicon crystal in 2D here. So there's silicon. I'm just gonna draw 9 atoms. So that's silicon. And then when we try to dope the silicon with a group 5, I'm just going to use phosphorus here, and I'm going to draw it in blue. So phosphorus. So I have a phosphorus here, and of course phosphorus has 5 valence electrons, so it has 1 more electron here. So for now at 0K, this is at 0K, the electron from phosphorus is still bonded by the phosphorus. Okay, why? Let's look at the energy band diagram. So we have a conduction band and a valence band, and then there's also a energy level here called the donor energy level, or ED. And at 0 Kelvin, there's all the phosphorus atoms here. You can see these are all the excess electron from the phosphorus. So as you can see here, there is 7. So this is as if there are 7 phosphorus dopants. So these electrons, they are bound by donor binding energy, or called En, which is of course equal to Ec minus Ed. So in order for these phosphorus atoms to be elevated or excited to the conduction band, they need to gain En of energy. Okay, so now that's at 0K, and then let's look at how it looks like if the temperature is larger than 0K. So now we have larger than 0K, so there's some heat already, and as the temperature increases, more and more phosphorus atoms get elevated. So let's say the temperature is still very low, so only 3 out of 5 of the electrons are elevated to the conduction band. So this is at a very low temperature, but as the temperature increases further, let's say to room temperature, all of the donor atoms, or all of the donor electrons have been elevated to the conduction band, and then now the donor energy level is ionized, so it's called fully ionized, and it's positively charged. So because originally all the electrons are here, which makes the phosphorus still neutral, but now when all the electrons have been excited to the conduction band, the phosphorus is now positive. So let's look at it in terms of structure now. So originally at 0K, the electron is still loosely bonded to the phosphorus, but now that the temperature is quite high, the electron have been elevated to the conduction band somewhere. So now the phosphorus, because it still has 5 proton but only 4 electrons, so now the phosphorus becomes positively charged. So this actually results in the creation of electron in conduction band. As you can see, there are electrons here in the conduction band, and there are still no holes in the valence band because there are no excess holes in the valence band, although there are creation of electrons in the conduction band, because the temperature is not high enough yet. So let's say at this room temperature, of course there are still some EHP generation, but these are EHP pairs, and there are still an excess amount of electrons in the conduction band without holes. So you can see for the ones that are elevated by thermal energy, they form an electron hole pair. But for the ones that are the result of the doping, there are so-called free electrons in the conduction band. Alright, so now let's look at p-type doping. So for this example, I'm going to use still silicon, but I'm going to use boron as the dopant. So of course this is originally still the silicon lattice. So now, instead of using phosphorus, which has 5 valence electrons, we are going to use boron, and I'm going to use green color for boron. So now we have a boron, and of course, because the boron only has 3 electrons, so there's like a hole. There's sort of a hole. It's not really. So there's a hole here at boron, and in order for there to be this, there's an acceptor. There's also an acceptor energy level. So instead of the donor energy level, we now have an acceptor energy level. So essentially, this is at 0K, and the acceptor level is empty. So in order for the electrons from the valence band to be elevated to the acceptor level, they need to gain an energy of EA minus EV, because there's a distance between the acceptor energy level and the valence band. So now let's look at how it looks like above 0K. So we have a conduction band, valence band, and then the acceptor energy level. So above 0K, some of the electrons from the valence band will be elevated or excited to the acceptor level. So now the acceptor level are filled with these electrons. So this is for the boron. So now the boron becomes negatively charged because originally when it's empty, it's neutral, but now there are electrons at the acceptor level. So now it is negatively charged. So the boron is negatively charged. So how this looks like is basically there's an electron here that is given to the boron to make it negatively charged. And let's say if it's given from this silicon atom, originally the silicon is like this, but now because this silicon gave an electron to the boron, now it has a hole here, because this electron, the green electron, comes from this black hole. So now that it gives to the boron, the silicon has one less electron, and now the silicon has a hole. So that's how the p-type semiconductor is. So of course at thermal equilibrium, we have the electron concentration in the conduction band is equals to the donor plus the whole concentration in the valence band. So this is so-called the donor concentration. So this is the number of phosphorus atoms, for example, in this case, the number of phosphorus atoms that are doped. Okay, so why is this the case? So as you can see, this is positive, and of course this is also positive because the hole is positive. The hole is the absence of electron, and then this is the negative. So the amount of negative is equals to the total number of positive. So this corresponds to the band diagram here, as you can see. So for the p-type, it's the same thing. It results in the creation of holes in the valence band without creation of electrons in the conduction band. So obviously, similar to the m-type, it's still positive. It's possible that there are still some electrons and holes in the conduction band, valence band, but this is separate, and then the the holes in the valence band is still like free holes, so there are no excess electrons here that creates these holes. So for the p-type semiconductor is just p0 equals to Na plus N0. So this is the acceptor concentration. So of course, this is negatively charged, this is negatively charged, and this is positively charged. So again, the total number of positive is equal to the total number of negative. And of course, since as you can see, because the donor concentration is significant as compared to the hole concentration in the valence band, which is P0, the majority carrier will be an electron. And then for the p-type, because the P0 is much larger than the N0, the majority carrier will be a hole. So yeah, that's a quick summary of the doping of N-type and p-type semiconductor. So now let's look at the donor binding energy of a semiconductor or N-type semiconductor. And the donor binding energy, as we have said earlier, is En, and it's given in the formula sheet that En is equals to this. The derivation of this equation is not necessary, but this is the reduced Planck constant. And this reduced Planck constant is equals to h over 2 pi, so the Planck constant divided by 2 pi, times the effective mass of electron divided by this. And this is just again, this is just effective mass of. That's why it's called Mn, because when it is doped with excess electrons, it's the N-type, so that's why it's called N. And then this is the relative permittivity of free space. Permittivity of free space. And then this is the relative permittivity of a material. So yeah, this is the formula for donor binding energy, and in this case, N is just equals to 1, 2, all the way to infinity. So that's the donor binding energy, and let's try to use this in example 3.1. Estimate the donor binding energy of gallium arsenide given that the effective mass of electrons Mn star is equals to 0.067 M0, and the relative permittivity of gallium arsenide is 13.2. So this is quite straightforward, so it's just subbing into the equation. So minus Q4 to power 4 and 2 4 pi h over 2 pi squared times 0.067, and then the elementary mass of electron 13.2 is a relative permittivity, and the permittivity of free space is this, so we can just square this, and then we have 1 over n squared. So if you type this in the calculator and work it out, you will get negative 8.34 times 10 to the power of negative 22 over n squared. And this is in joules, so we can convert this to electron volts, and this happens to be this. So that's the donor binding energy of gallium arsenide, which is negative 5.21 over n squared milli electron volts. So what exactly is N is? We can use this in an example here, which is energy required to excite electron from ground state to free state N infinity. So because it's 1 to infinity, the energy required is 5.21 milli electron volt. Because when n equals to 1, because when n equals to 1, the binding energy is this, and then when n equals to infinity, it's 0. So it's 5.21. So 0 minus this is equals to 5.21. So now let's look at the temperature dependence on the carrier concentration on semiconductors. So here we have an N-type doped silicon semiconductor with a donor concentration of 10 to the power of 15 atoms per cm cube. And of course, this graph is exactly only for this combination. And for different semiconductors or for different doping, concentration can be slightly different. But we are just going to look at this in general. So for 0 to 150K will be around the free sub-region, 150 to 450K is the extrinsic region, and above 450K is the intrinsic region. So although I can say that this changes, but it's still quite similar for most semiconductor and doping, because they are designed to work in the extrinsic region, which is containing the room temperature of 300K. So let's just look at it this way, which is quite accurate. We're just going to reference the equation we have gotten earlier, which is N0 equals to ND plus P0. So we are going to start from the free sub-region here, where the electrons at the donor level begin to be excited to the conduction band, but little electrons in valence band are excited to the conduction band. So this is the donor energy level. And this means that some of them are being excited to the conduction band, while many of them still remain in the donor energy level here, and very, very little electrons in the valence band are being increased or elevated, excited to the conduction band. Why is this so? It's because that the band gap energy is much larger than the donor binding energy. So as you can see from the example earlier, we have seen that the donor binding energy is like a few milli electron volts, while the band gap is like 1 or 2 or 3 electron volts. So you can see that the band gap energy is much larger. So a lot of the donor atoms will be excited to the conduction band, but very little electrons in the valence band will be excited to the conduction band. So it will be something like this: N0 equals ND plus P0. That's why ND plus means that ND is larger than P0, because because of this. So this is the equation for free sub-region, and we'll look at the extrinsic region. So at the extrinsic region, all of the donor atoms have already been ionized. So all of them has already been excited to the conduction band. And then there's no more electrons left in the donor level. And then some very, very little still very little electrons in valence band are being excited to the conduction band, again because the band gap is just so much larger than the donor binding energy. So in this case, we have, because all of the electrons in the donor energy level is already excited, so the donor concentration is much larger than the whole concentration in the valence band. So because the ND is much larger than the P0, we can sort of ignore the P0 because it's orders of magnitude larger. So we can ignore it, and then we can let N0 is approximately equals to the ND. So for an extrinsic region semiconductor, you can estimate the electron concentration in the conduction band, which is N0, to be approximately equals to the donor concentration, which is ND. Of course, this also depends on the intrinsic carrier concentration and things like that, but this is a quite good approximation most of the time. And for the intrinsic region, which is larger than 450K, many electrons in the, okay, not E, oh, I drew this wrongly both. So this is EV. So many of the electrons in the valence band have been also excited. So you can see we can have many holes here, and then all of these holes have been excited. So there are like many electrons here. So of course the number of electrons in the valence band and the number of holes in the valence band is much larger than the number of dopant atoms. So P0 is much larger than ND. And because at this high temperature, most of the electrons, or a lot of the electrons, have enough energy to already bypass the band gap. So because of this, the equation up here becomes N0 is approximately equals to P0. So at above 450 Kelvin, you can see that because it's so much larger, orders of magnitude larger, it's essentially already back to intrinsic semiconductor. Recall that we have said earlier in this video that the intrinsic semiconductor is where N0 equals to P0. So above 450K, the doping is very ineffective because it's so hot that all the electrons in the valence band are already excited to the conduction band. So it's sort of back to already an intrinsic semiconductor. So you can see it's approaching the intrinsic carrier concentration. So that's why many silicon semiconductors are rated at around 175 or 170 degrees Celsius of max operating temperature, because you can see this translates to around 450 Kelvin. So that's just before it reaches the intrinsic region where the doping becomes ineffective, and the semiconductor, or of course, loses its the desired electrical properties. So that's why that's the maximum operating temperature of many silicon semiconductors. Or okay, maybe not operating temperatures, but rather junction temperature, because the semiconductors are held with let's say epoxy or other maybe thermoplastic packages that cannot withstand such a high temperature, but the junction temperature is normally rated at around this temperature because of if it exceeds this temperature, it will reach the intrinsic region. So yeah, this is the end of part 3 of this video series about doping, and if you enjoyed it, please check out the other videos in the same video series, and have a good day.